Hello, everyone, and welcome to another episode of Chemistry. Today's lesson is about energy. In this chapter, you will learn about thermochemistry, which is a small part of a larger field called thermodynamics. Thermodynamics is the study of energy and temperature changes, and thermochemistry is the study of the relationship between chemistry and energy. More specifically, it's the study of the chemical reactions and energy changes that involve the transfer of heat. For example, ice melts in water because heat is absorbed by the solid ice. In other words, heat is transferred from the liquid water to the solid ice. Likewise, the transfer of heat can also be observed in a multitude of chemical reactions. They can either absorb or release heat. In one of the previous chapters, you learned that there are two types of reactions involving heat. An exothermic reaction or process is the release of heat, whereas an endothermic reaction or process is the absorption of heat. The formation of rust, for instance, is an exothermic process, while photosynthesis, the synthesis of sugar, is an endothermic process. Energy, by definition, is the capacity to do work. And work is defined as the result of a force acting through a distance with the equation W equals force times distance. Let's say there's a big heavy box on the floor. If you're trying to push the box and the box doesn't move an inch, then you haven't done work. But once that box moves to a certain distance, then you have performed work. And work is a type of energy that can be quantified using this equation. There are two main types of energy, kinetic and potential. Kinetic is the energy of motion. Anything that moves has kinetic energy. Potential energy, on the other hand, is an energy associated with position or chemical composition. Thermal energy is a good example of kinetic energy. It's the energy associated with the temperature of an object or a given system. This energy results from the movements of atoms or molecules within a given substance. Chemical energy is an example of potential energy. This is the energy associated with the relative positions of electrons and nuclei in atoms and molecules. Thermochemistry is already a big field in chemistry, but it's only a small part of a much bigger field called thermodynamics. And thermodynamics has 4 laws. The first law of thermodynamics is basically the law of conservation of energy, which, as you already know, states that energy is conserved. Energy is neither created nor destroyed. Another way to put this is that the total energy of the universe is constant. That's the first law of thermodynamics. Energy may not be created nor destroyed, but it can be transferred from one object to another or can be converted from one form to another. You can convert potential energy to kinetic, thermal to electrical, or even electrical to mechanical energy. When we study the transfer of energy from one object or system to another, we need to know 2 things: the system and the surroundings. The system is basically the thing that you're studying. That could be something physical, tangible, and visible like objects, or something that we can't see with the naked eye like chemical reactions. The surrounding is everything else but the system. This could be the glassware you're using, the air around us, the bench, etc. Something that's in proximity where the system could easily exchange energy with. Here's a schematic illustration showing you that energy can be transferred from the surroundings to the system and vice versa. Energy can go in and or out. In a perfect and well-controlled environment, when the system loses energy, the surroundings would gain that same amount of energy. Here's an example. Let's say you're conducting a simple experiment on a lab bench. There's air molecules everywhere. There's the bench, and the beaker contains the chemical reaction. Let's say that this is an exothermic reaction, which means heat energy is released. Since water, H2O, is usually not part of the chemical reaction itself, it's considered part of the surroundings, which also include the bench, the glassware, and the air molecules. So in that case, this exothermic reaction shown here can exchange heat with the surroundings. Heat can be transferred to the water molecules, the beaker, the bench, and the air molecules. Before we move on to the main topic, let's look at the different units of energy. You have learned in the past that kinetic energy is equivalent to 1/2 mv squared, where m is the mass in kilograms and v is the velocity in meters per second. So using this formula, kinetic energy would have the units kilogram meter squared per second squared. 1 kilogram meter squared per second squared is equal to 1 joule, which is another unit of energy. 1 joule is actually relatively minute in thermochemistry, and so kilojoules is more appropriate and more commonly used. Calorie is another unit of energy. So when you work out at the gym or do cardio, you're burning calories, which means you're using up your energy. There's a difference between big C calorie and little c calorie. 1 big C calorie is equal to 1,000 little c calories. The food industries in Europe, Asia, South America, and others use kilocalories instead of big C calories, just to prevent that confusion between the big and the little calories. Kilowatt hour is another common type of unit of energy, which represents electrical energy. Next time you see your electric bill, look at how much energy you've used in kilowatt hour. Most likely, it's in several hundreds of kilowatt hour to a few thousands. 1 kilowatt hour is equivalent to 3.6 times 10 to the 6 joules. Liter atmosphere has a symbol LATM, and 1 liter atmosphere is equivalent to 101.3 joules. Let's look at a few energy conversion examples here. Convert 212 kilocalories to joules and kilojoules. So the first step is to write down what's given. Then set up your dimensional analysis. Here you can see that kilocalories cancel out. Add another train track here to convert calorie to joules. And this gives us 887,000 joules, or 887 kilojoules. Next one here, convert 47.3 kilojoules to calories. Set up your dimensional analysis where 1 kilojoule equals 1,000 joules. Then add another train track converting joules to calories, and this gives us 11,304 calories, or 11,300 calories with proper number of sig figs. And the last one here, convert 6.34 times 10 to the 8th joules to kilowatt hour. Set up your dimensional analysis as shown. Joules cancel out, and we get 176 kilowatt hours. So how do we apply this energy concept and the exchange in energy in chemistry? First, you have to understand that the chemical reactions themselves are the system, and everything else is the surrounding. In a chemical system where you have reactants turning into products, the reactants are the initial state, and the products are the final state. You start out with the reactants and you end up with the products after the chemical reaction. So quantitatively, the change in energy of the system is the difference in the energy of the final state and the initial state. In other words, it's the difference in the energy between the products and the reactants. Here's an example where carbon is reacting with oxygen to form the more stable carbon dioxide. Molecular compounds like CO2 are generally more stable than atomic and molecular elements like carbon and oxygen gas. So when you compare and graph their relative energies, CO2 is less than the carbon and oxygen combined because it's more stable. The carbon and oxygen have a higher energy than carbon dioxide because they are less stable and therefore more reactive. Because of this, the formation of carbon dioxide gas is said to be more energetically favorable. And so, because the energy of the reactants is greater than the energy of the products, the change in energy of the system, meaning the chemical reaction, will be less than zero or negative. And this means that there's extra energy released or given off by the chemical reaction, hence an exothermic reaction. But the question is, where does this energy go? The chemical reaction itself, as I've mentioned earlier, is the system, and the system can exchange energy with its surroundings. And so because the delta E, or the change in energy for the system, is less than zero or negative, energy is being released to the surroundings. And because the surroundings receive that same amount of energy, the delta E, or change in energy for the surroundings, is greater than zero or positive. Mathematically, the delta E of the system is numerically equivalent to the delta E of the surroundings. The only difference here is the negative sign. This negative sign indicates that the energy is being released or given off, and the other receives or absorbs it. Looking at the same combination reaction earlier, except this time in reverse, meaning the decomposition of carbon dioxide. Graphically, you can see that the carbon dioxide molecule is intrinsically lower in energy and more stable than the elements. The difference here is that now we have the carbon dioxide as the reactant and the elements as the products. This means that the sign of the delta E of the system would change. This time it will be greater than zero or positive. This means that energy must flow into the system in order for this chemical reaction to occur. A chemical system can exchange energy with its surroundings through heat and work. Both heat and work are two different types of energy, which can be quantified and determined mathematically. The symbol for heat is the letter Q, and W for work. Delta E is the change in energy, and this is equal to heat plus work. It's important to indicate the sign of energy, positive or negative. If energy is going into the system, whether it's through heat or work, we give it a positive sign. And if the energy is given off by the system, we give it a negative sign. Think of it like energy is being added if it's entering the system, or subtracted if it's leaving the system. Here's a summary of the different sign conventions of energy. If heat enters the system, it's positive, otherwise negative. If work is done or performed on the system, it's positive. If work is done by the system, then it's negative because you're spending energy to get the work done. And finally, if there's energy entering the system, then it's positive, otherwise negative. Let's look at some examples here and apply the concept. A small sample of propane burns, producing carbon dioxide gas and water, or water vapor. As the hot gas mixture expands, it releases 20 kilojoules of heat and does 31 kilojoules of work, pushing against a piston. What is the total amount of energy released in this reaction? Since it's asking for the total amount of energy released, given the amount of heat and work, we can use this equation shown here. Since heat was released, we give it a negative sign, negative 20 kilojoules. And because work was done by the system, the chemical reaction, we give it a negative sign, negative 31 kilojoules. Plugging these numbers into the equation gives us negative 51 kilojoules. Again, the negative sign indicates that energy was released in the amount of 51 kilojoules. Here's a few more examples. Find the total change in energy. For the first one, a gas absorbs 20 kilojoules of heat and has 30 kilojoules of work done to it. Since the gas absorbed heat, we give it a positive sign, positive 20 kilojoules. And because work was done to it, we give work a positive sign as well, plus 30 kilojoules. And this gives us 50 kilojoules of energy. Second problem here, a gas releases 30 kilojoules of heat and does 45 kilojoules of work on its surroundings. Since the gas released heat, we give it a negative sign, negative 30 kilojoules. And because work was done by the system, we give it a negative sign, negative 45 kilojoules. And this gives us negative 75 kilojoules, which means energy was released. Now let's look at what you just learned in full summary. So we have a system, which in chemistry is typically defined as the chemical reaction itself. This system can exchange energy with its surroundings. Energy can come in and enter the system, and likewise, energy can come out and leave the system. When energy goes into the system, we consider that an endothermic process, and exothermic when it's leaving the system. These are the sign conventions, and here are some examples of an endothermic process: melting, evaporation, and sublimation. These are the sign conventions when energy is leaving the system. And here are a few examples of an exothermic process: freezing, condensation, and deposition. Describe the following changes as endothermic or exothermic using the frame of reference given. Go ahead and pause this video and think about these problems. The first one here, water boils, converting to steam. The system here is water. Because heat is going in to boil the water, it must be an endothermic process. Second problem here, an acid and base react, releasing heat. The system here is the acid and base molecules. Since heat is leaving the system, it must be an exothermic process. And the last one here, a log burns in fireplace, and the system is the log. Since heat is also released when burning wood, it must be an exothermic process. So how do we quantify this heat that's being absorbed or released by the system? We can calculate this amount of energy using this energy shown here. We can calculate this amount of energy using this equation shown here. Q is the symbol for heat and has the unit joules. M is the mass in grams. And CS is the specific heat capacity, or just specific heat, in joules per gram degrees Celsius. And finally, delta T is the change in temperature measured in degrees Celsius. Heat capacity with the symbol capital C is defined as the amount of energy required to raise the temperature of a substance by 1 degree Celsius. There are two types of heat capacity. The first one is a specific heat capacity with the symbol CS. And by definition, this is the amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. The second type of heat capacity is known as the molar heat capacity, with the symbol Cm, which is the amount of heat required to raise the temperature of 1 mole of substance by 1 degree Celsius. You can always convert specific heat capacity to molar heat capacity and vice versa, as long as you know the molar mass of the substance. Heat capacity is equivalent to the mass of the substance times its specific heat. By substitution, heat is equal to heat capacity times the change in temperature. Metals like copper, silver, and gold have lower heat capacity than nonmetals and molecular compounds. For instance, copper and gold metals have specific heat capacities less than 1, whereas water is 4.184. This means that it would take a whole lot more energy to heat up water compared to the metals with the same mass to reach a certain temperature. This is also the same reason why it takes much longer to heat up water than the metals. Let's look at an example here. How many kilojoules of heat are required to raise the temperature of 120 grams of water by 5 degrees Celsius? We can use this equation to solve for heat. We have the mass of water, which is 120 grams, the specific heat of water, which is 4.184, and the change in temperature, which is 5 degrees Celsius. Here you can see the units canceling out, and we get 2,500 joules, or 2.5 kilojoules. Here's another example. When filled with water, a large reaction vessel in a chemical plant has a heat capacity of 5.41 times 10 to the 5th kilojoules per degree Celsius. How many kilojoules of heat are required to heat this entire vessel from 25 degrees Celsius to 48.2 degrees Celsius? Looking at the same equation here, CS is the specific heat capacity of water, which is 4.184. Since we are given heat capacity of 5.41 times 10 to the 5th, we can use this equation shown here which is Q equals heat capacity times delta T, which is the change in temperature. All we have to do now is plug in the numbers, and we get 1.26 times 10 to the 7th kilojoules. Here's one last example. If 400 joules of heat flow into 100 grams block of chromium, how much will the temperature of the block rise? The specific heat of chromium is 0.449 joules per gram degrees Celsius. Here's the equation that we will need. We are given the mass, the amount of heat, and the specific heat of the metal. Now we have to find the change in temperature, delta T. We can solve for delta T by isolating it. Divide both sides by mCs, and we get this equation for delta T, which is equal to Q divided by mCs. All we have to do now is plug in the numbers, and we get 8.9 degrees Celsius or 9 degrees Celsius with proper number of sig figs. So experimentally, how do we measure this exchange in energy or transfer of heat? There's a method they call calorimetry, and they come in many different types. The one you will learn here is the simplest type, called coffee cup calorimetry. This method quantifies the amount of heat that's generated or absorbed by an object or a chemical reaction at constant pressure. This is what a coffee cup calorimeter looks like, where you have two nested styrofoam cups, a stirring rod, and a thermometer to keep track of the change in temperature. Imagine we have a hot piece of metal submerged in cold water inside the cup calorimeter. Because heat is always transferred from a hot object to a cold object, the metal releases heat as the water absorbs that same amount of heat. So, to quantify this amount of heat that was transferred, we can use this equation shown here, where Q, water, equals negative Q, metal. In other words, the heat absorbed by the water is equivalent to the heat lost by the metal. We know the formula for heat, as shown here. If we know the mass of the water and the metal, as well as the change in temperature for both the water and the metal, we can use this formula to calculate the specific heat capacity of that metal. Let's look at an example here. Let's say we have a block of nickel submerged in water inside the calorimeter. The mass of the nickel is 26 grams, with an initial temperature of 100 degrees Celsius. The water inside the calorimeter weighs 52.1 grams, with an initial temperature of 20 degrees Celsius. So we have a hot metal being submerged in cold water, so heat will be transferred from the metal to the water. The final temperature is something we can measure using the thermometer. At some point in time, the water in the metal reaches an equilibrium temperature of 24 degrees Celsius, which is the final temperature. Calculate the specific heat of the metal. We can use this equation to find the specific heat. The change in temperature of the water is 4 degrees Celsius and negative 76 degrees Celsius for the metal. We know the mass of the water in the metal, as well as the specific heat of water, which is 4.184. Plug everything into the equation, and we get 0.44 joules per gram degree Celsius. Here's another example. A 50-gram block of an unknown metal with an initial temperature of 100 degrees Celsius was submerged in a coffee cup calorimeter containing 50 grams water at 24.8 degrees Celsius. Both the metal and water reach an equal temperature of 51.2 degrees Celsius. What is the specific heat of the metal? Here we're given the mass of the metal and its initial temperature. We're also given the mass and initial temperature of the water. The final temperature reached 51.2 degrees Celsius. We can calculate the specific heat of the unknown metal using this equation. We can easily calculate the change in temperature for both the metal and the water as shown here. Plug in all the numbers, and we get 2.26 joules per gram degree Celsius. And that's the end of chapter 8. Thank you for watching, and if you like this video, Please subscribe, and I'll see you next time.